Review of the Thermochemistry Unit of Chemistry 30, which does follow the Alberta's curriculum, but it does overlap quite a bit with most of the curriculums throughout Canada, and also if you're taking a senior level chemistry course in the States. So when we're looking at our Thermochem unit, the first thing we start with is talking about this formula here, Q equals MC delta T. This formula, definitely, you do want to pay attention to units. Sorry, I was just trying to circle it. But Q is always going to be in joules, and then your mass is going to be in grams. When you multiply it by your C value, that's unit is joules per gram degree Celsius, and that's oftentimes a given value, or you'll be finding it. And then you're changing it by the temperature, which is your change of Celsius. With this value, your specific heat capacity, if you are not given it directly, or if you're not finding it, then it is going to be on page 3 of your data booklet if you're in the Alberta curriculum. So there's a few listed there, like copper, aluminum, iron, and so on. When you're going to use this formula is when you're taking a look at an object that is gaining or losing heat. So to emphasize the Q equals MC delta T formula, you are not a chemical reaction. So you're either heating a substance up, so like heating a substance in the oven, or cooling a substance down, like putting a substance in the fridge. So it's not a reaction. A common question throughout curriculums is, where does energy originate from? And the energy always originates from the sun. The other part of this that you'd want to know is how we go from the sun to getting fossil fuels. So we do want to know this process. So you start with the energy from the sun, then you have photosynthesis that can harness that sun energy. Then after many years, we'll have that decay, and that decay is what causes us to have those hydrocarbons. And then you can harness those hydrocarbons, which would eventually lead to gas in your car. So do know this process. You do also want to know this reaction for photosynthesis, just like you would for cellular respiration. Now, this is a couple old diploma questions that we'll take a look at, and it is very wordy, and if you take your time and read it through, and with that information given, it might look like Hess's law short to begin with, but then when you look at the question and it's asking about the original source of energy, we would know to pick A, because the original source is always from the sun. Looking at the next one, similar idea. We have some information happening, but looking at the original source, it doesn't really matter what the question's about, because your original source will always be the sun. The next one, looking again, it will be something to do with the sun, but just having that idea, and we'll look more into endo and exothermic in a second, but hopefully you have a good understanding here. And this is talking about methane being burned. So we have a combustion reaction, and if something is being burned and it's combustion reaction, you're going to give off heat. So that means you are an exothermic reaction, so you can rule out the first two. And then the original energy source would be the sun. So this answer would be D. So these were old diploma questions, and old diploma questions, they do look similar. So if you have that good understanding, you should be able to continue and see questions in the future that might be similar. Now, as we moved on in Thermochem, sorry about that. As we moved on in Thermochem, then the next thing we started to take a look at is the term enthalpy and molar enthalpy, and we need to know when to use each of these terms. So the next formula we have is NH equals delta H, and here the units, we do know N is still what you're used to. That is going to be moles. This H on the left-hand side of the formula is a molar enthalpy. So it does amount or depend on the amount of moles within an equation. And then the kilojoules on the right-hand side, that's your energy released or absorbed to the environment. So this can get a little bit confusing, because even though this variable is H, it can come from the delta H of the reaction. So that's just to keep in mind. And if it's not given to you, that molar enthalpy, then we might have to find it, and that would be using Hess's law. So taking a look at this one before we get into some harder questions, here we have a chemical reaction. You do have that enthalpy given. It's on the product side. So if you took that out of the equation, because it's on the product side, you would make it negative. So negative 954 kilojoules is the enthalpy of this reaction. And if it's asking for molar enthalpy of the NiO, the nickel oxide, that would represent the equation, this part here. And within this balanced chemical equation, this value depends on 3 moles of the nickel oxide to be present. So when we're taking a look at the molar enthalpy of this reaction, you would take that enthalpy and divide it by the amount of moles you have, and then we would see your answer here would be C. So always depending on moles, so we need to know what it's asking about. Now, this next one we're looking at, we have this combustion reaction. We have the enthalpy of the reaction. We know it's exothermic once again. And this one's asking for the mass of methanol that burns to produce an enthalpy change of negative 9.00 times 10 to the power 4 kilojoules. So we are going to use the formula NH equals delta H. Anytime energy is being produced or absorbed, that is the delta H value. So this negative 9.00 times 10 to the power 4, that's going in for delta H. It's asking about methanol. So the molar enthalpy, this H value, we're getting that from the reaction, but you're going to have to divide it by 2 because there's 2 moles of methanol that this reaction is representing. So we can fill in those values, and then we want to solve for N. So if I wrote this out, I'll have N times, and it would be negative 1,275.8 kilojoules divided by 2 moles. And then this will equal negative 9.00 times 10 to the power 4 kilojoules. So we want to isolate N, so we can divide both sides by what we have in the bracket. And I'm quickly just going to plug this into my calculator. And you could do the same if you have a calculator handy, just because it's always important to know how to use your calculator. So I have my negative 9.0 times 10 to the power 4. And then I'm going to divide it by, and I can do this in one step if I keep my brackets. Sorry. So I'm just going to plug that in, divide that by 2. And I'm solving for N 141.08. And there are more values. I'm just going to keep it in my calculator, and that would be for moles. Now, because it's asking for mass, I need to remember to go from mass to moles. I always will have the molar mass. So I'm going to multiply by the molar mass of methanol. And I just will need to calculate that from my data booklet. I'm very sorry. So I'd add my 1 carbon, and then I have 4 hydrogen total and 1 oxygen. So taking a look at what's present, adding up everything, my molar mass was 32.05. So I can now take that value and multiply it by the 141.08. And again, I didn't want to round that, so I'm just using the value that's in my calculator. And the answer I'm going to get is pretty large. It is 4,521. And then there's the decimals 86, and then that number goes on. And that's in grams. But to answer this question, I needed kilograms. So I'll just take that value and divide it by 1,000. And then I will keep 3 significant digits because this value I'm seeing given in the question has 3 sig digs. So my answer would be 4.52 kilograms. So that would be my total answer from this question. Okay, so there's another similar question here. And with this one, it is the same idea. They're asking the enthalpy change for 1 mole of H2S, which is up here. And again, if you want that change in enthalpy, you are using that formula NH equals delta H, and you do want to figure out that delta H. Then going from the question, you're given delta H, but that goes in for H, and this value is dependent on moles, and it's asking about the H2S, and this equation represents 8 moles reacting. So you'd want to divide that by 8. So when you're filling this in, it's giving you this value 1 mole, so it would be 1 mole times that negative 1,769.6 kilojoules divided by 8 moles, and we'll plug that into our calculator. And now this question is also showing that you can put your answer into scientific notation and answer in that particular format of A dot BC times 10 to the power of D. So I'm just plugging this in. I'm getting the value of negative 221.2. So if I turn this, and this would be kilojoules, if I turn this into scientific notation, I would have negative 2.21 times 10 to the power of 2 kilojoules. And so my A, B, C, and D, filling that in, my A would be 2, my B would be 2, my C would be 1, and my D would be 2, the exponent. Okay, so here's another question. If you wanted that practice, you can take a look at it. I can explain it, but we'll just skip it for now. Again, another practice of NH equals delta H. With this question first, you would have to turn your grams into moles using your molar mass. And then you would take that negative 251, that would plug in for H. Here, you're not dividing by anything. Well, you would be. You'd be dividing by 1, but that's not going to affect your calculation because this value would be representing 1 mole. So from grams, you can get moles. From the equation, we have H, and then you could figure out how much energy is produced. So moving on from there, and we've talked about it a little bit with the examples we've seen, there are 2 ways you can communicate enthalpy change. One was within the equation. So depending on what side, is it on the reactant side or is it on the product side? The other is to have delta H written beside the equation. So the 2 things you want to recognize is if your enthalpy is on the reactant side, or if it is positive as a delta H, your reaction is endothermic. You are absorbing heat from your environment. If you have your enthalpy written of the product side of the equation, or it's negative, then it's an exothermic reaction, meaning you're giving heat off to your environment. So looking at this question, you have a series of reactions. On equation 1, you have an endothermic because it's on the reactant side. Equation 2, exothermic. Equation 3, exo because it's negative. And equation 4, endo because it's positive. With this one, we're ranking from absorbing the most energy to releasing the most. So if it's absorbing the most, you're looking for the most positive. And if it's releasing the most, you're looking for the most negative. Now, this is also asking per mole of carbon dioxide. So we want to make sure the equations are representing 1 mole. So for instance, the first 2 equations, they do have 1 mole, but the next 2 equations, you have this 2 here. So the value you're given, you'll have to divide by 2. And this last time you have a 3. So the value you're given, you'll have to divide it by 3. So if we start to rank from most absorbing of energy to least, then if we divide this value by 3, we get 124.7. So this would be the most endothermic. So equation 4 would go first, then 1, and then looking at this last 2, if I divide negative 514.1 by 2, it's going to be larger than this 41.2. So that would be my last one, most release, which would make 2 the second last. So just going through it and being able to understand the values from largest to smallest. Taking a look at this old diploma question, similar idea. You have a balanced equation. It wants to know which one is balanced and which sign would work. So we would just go through and double check the balancing. We definitely know if it's a combustion reaction, then you're giving off heat. So it's not going to be B, it's not going to be D. So now we would just check the balancing. So I actually don't have this written down, so I'm just taking a peek at it quickly. I have 2 carbons on each side. If I look at equation 1, 6 hydrogens, and 7 oxygens. 4. So unless I did something wrong, it looks like it's A. So just double checking. So 2 carbons on each side. Then you have 5 hydrogens from this first part here, plus this hydrogen on the end, which makes 6. Then 3 times 2 gives you 6. So the last thing I want to check is my oxygen. So on the left-hand side, I have 3 times 2 is 6, plus 1 is 7. On the right-hand side, I have 2 times 2 is 4, plus 3 times 1 is 3. So that's also a total of 7. So it looks like our answer here is A, just with double checking our balancing. And looking at this next one, so here we have a little bit of information. So we have sucrose, and it's giving us some information about, again, a combustion reaction that's burning some sucrose. So what we're going to look at here, it's saying if we included this as a term in the above equation. So if it is a combustion reaction, again, you're most likely giving off heat, which would make your reaction exothermic. I am not sure why that just happened. So that would make your reaction exothermic. And if it's exothermic, you would want to be on the product side. So we can rule out A and B. And then the next part is water in the calorimeter. Now, the water itself is not undergoing a reaction, so that would be kinetic change. So that would be C. The water would start to be, if it's getting heated up, would be moving faster, and movement would be kinetic. If we had asked about the sucrose, and that's what's undergoing the chemical reaction, then we can pick potential, but it asked about the water. Okay, so here's a similar question, just again showing that we understand, and this is old diploma questions. So if you read this over, why does that keep happening? I am very, very, very sorry. Wow, I think we got towards the end there. There we go. Sorry. Here we go. So old diploma questions. Here we go. They're the same. So I'm just really taking a look at this value here. It's negative, so energy would be released to the environment. So taking out A and B. And then if you included it in the equation, it would have to be on the product side because it's exothermic. Similar question, looking at this equation here. Looking at this value, if we took it out of the equation, it would be negative, or the fact that it's on the product side means it's exothermic, so looking at C and D. And when we're looking at exothermic reactions, if you looked at a potential energy diagram, all exothermic reactions follow this drop in energy. And we can use that to help us with the next part of the question. So just comparing it, reactants would have a higher potential energy because it would be higher up on the graph than the products. So our answer would be C. Okay, so that's to start. If your enthalpy wasn't given to you, then there are 2 ways to find it. One of the ways is to use Hess's law short. The other way is Hess's law long, depending on what information's given. So to use Hess's law short, we're using standard heats of formation. It's just this tablet is so sensitive. Well, that's where I need to be. So if you're using Hess's Law Short and you are in Alberta, you have a bunch of heat of formations listed on page 4 or 5 of your data booklet. If you're not in Alberta and you do have a data booklet, I'm just guessing it would be on a different page. Now, understanding heats of formation, this means you have a formation reaction. So when you have energy related to this and when we can use it is taking a look at like how water's being formed. We know energy by, or elements by itself are just 0, and then the formation is the value you would get from the data booklet. And one thing to note here is that if you have a decomposition reaction, you would be reversing the reaction, and if you were to do that, you just reverse the sign. Now, the formula here is the delta H of the reaction. You get the total of the delta H of the products, and you subtract the delta H of the reactants. So if I took a look at this one here, there's some information given. We have a couple delta H's, and then they're giving us the molar enthalpy for the formation of a solid azide, and it is positive 21.7. Then they want to know the enthalpy change of reaction 1. So here, when we're taking a look at it, if we're taking a look at this reaction, this is a decomposition reaction. So that's one thing we'd want to note. So because it's the same formation and equation 1 is not showing formation, we'd want to flip this reaction either to match it or flip this sign to represent a decomposition reaction. And that's what we're going to do since it's asking for equation 1. Now, all molar enthalpies for formation represent 1 mole being formed. Here, 2 moles are being decomposed. So you'd want to take this value and multiply it by 2. And here, then, that gives you your answer as A. So this is not quite Hess's law completely, but we're getting there. We're just kind of leaning into it. Looking at this next one, it's giving us some information, giving us a delta H value, and asking us the molar enthalpy for formation of CS2. So from within this equation, we want to figure out if this was in your data booklet, what would be the heat of formation. So what you can do just to start is writing down enthalpies you know. So if you look up sulfur trioxide, just taking a look, and then you do want to pay attention to the state of this one. So this would be the vapor. You would have negative 395.7. And now this is kilojoules per mole. So we would take this value and multiply it by 2 because we have 2 moles of that sulfur trioxide. Then carbon dioxide, taking a look at that one, carbon dioxide has an enthalpy of formation of negative 393.5. This CS2, that's what we want to find, and elements that are by themselves have an enthalpy of formation of 0. So we can still say we're multiplying this by 4, but that won't really help us too much. Then when we go to do our calculation, the delta H of the reaction is going to equal the delta H of products, the sum of all the products, minus the delta H of the reactants. So in this case, we know the delta H of the reaction, so we can write that down. So positive 1,301.6, 6 kilojoules. And then we'll need to get a total, not for our products, for our reactants. So here we would have 0, we just don't even have to include it. So you just have your CS2 that we want to solve for, and we're going to subtract the delta H of the reactants. So if I quickly put that into my calculator, 95.7 plus negative 393.5, I get a total of negative 1,184.9. So now I just want to solve for CS2. So if I have a negative and I'm subtracting, if I'm subtracting a negative, that would become positive. And then I just want to move that value to the other side. So I'd have 1,301.6, and then I would end up subtracting 1,184.9. And I have a positive value of 116.7. So this is using Hess's law short to find an enthalpy of formation within. This one with the molar enthalpy of combustion of propane. Again, just to save a little bit of time, I'll just explain how to set this one up. Because it's asking for the combustion of propane, if you look propane up, you will get a value. So delta H of the formation of propane is negative 103.8. So be careful with that, because that is going to try and confuse you by giving this as an answer, as a distractor. So this value represents the formation. So propane is C3H8. So if carbon came together with hydrogen to form propane, we can use this value if it was a formation reaction. But it's asking for the combustion reaction. So instead, you want to take that C3H8 and you would add in oxygen, right? Because that would be combustion. And that will always give you water and carbon dioxide as a gas. Now, with this part here, I actually probably should have kept this in the gas state. That can be a little bit tricky. What I tell my students is assume gas unless it tells you otherwise. So if we were in a closed system, we would put a liquid. But if it doesn't say you're in a closed system, assume open system. Now, before you go to apply Hess's law short, you would need to balance this reaction. So if you went to balance this out, we would need to balance our carbons with a 3. We would need to balance our hydrogens with a 4. And that would bring us to 10, so a 5 for oxygen. Now that we have that, now we can start to write in some values. So now the value for the heat of formation, you would be using this value for your propane. Oxygen would be 0. You would look up the formation value for water and for carbon dioxide, and try not to forget to multiply it by the amount of moles you have. And then you can apply the formula. Delta H of the reaction would be the delta H of all your products, subtract the delta H total of your reactants. So just moving on from here, again, similar question with this one, just to describe it. I'm not sure why that keeps happening, and again, I apologize. With this question here, it is asking you for enthalpy change. Sorry, I didn't mean to cross that out. But what that means, we are using that formula NH equals delta H for this reaction. Enthalpy change. Oh, I'm sorry. Nope, I'm wrong. I needed my other notes in front of me. We're not asked for heat released or gained. What we're asked for. Maybe I'll just pause this here because this keeps happening, and then I will try and upload a different video with the rest. I hope you enjoyed this video. I hope you found it helpful, and I will be looking at the second half shortly.